Okay, so the problem that we're going to be investigating today is a searching problem. And I think we need to do more searching problems because I think it's a good topic to become sound in. And what we are going to look at is how do we search a two-dimensional matrix that is sorted. So there's two variants to this problem that we're going to address. We're going to address this one, and then there's going to be another one that I'll describe. So here's how it goes. We have a two-dimensional matrix. I excluded the brackets here, but you get an array of arrays. And what you need to do is you need to find an item. And the special property of the matrix is that every row is sorted. Every row is sorted. Every row is sorted. There's a reason I keep saying sorted, because anytime you see the word sorted, you immediately think my optimal solution will be logarithmic. Somehow, some way, if there is not a logarithm in your final solution, it's probably not the most optimal solution, given that the array is sorted, or if it ever has a sorted property, you know? It's just a pattern you notice. And whenever you see sorted, always think this is gonna go towards binary search. But we're not gonna get there yet. We're gonna go towards the thought process and thinking about this. But what we see is the rows are sorted. A special property about this matrix is that the last element of every row is less than or equal to the first element of the next row. So look at that 3. That 3 is less than or equal to 4, right? It's less than or equal to the first element in the next row. So, okay, let's think about this. When I'm thinking about searching, immediately, brute force it. We are looking for an item. Say we're looking for 5. What could we do? Well, we could look at every single item in the matrix. That's going to entail doing m times n time. I've given us the columns. We have n columns, 4 columns. We have m rows. We have 3 rows. And what I want you to see is if we search every single element in the matrix, we touch 12 elements. M times n, 4 times 3. We upper bound to the rows times the columns, m times n. Now this is one way we could do it, but I mean this is obviously not what our interviewer would want, because we got a very special propertied matrix, very special. And there's no way it would be this simple, right? So let's think a little more. So I said binary search. We're computer scientists. We know about our logarithms. We know about our sorting algorithms and our searching algorithms. So we can think a little harder. We can be smarter than this, right? So what we can actually do is, why don't we do a binary search in every row? I mean, that makes sense. Every row is sorted, right? If every row is sorted, if we do binary search, we maintain the invariant that if we chop a search space in half, the search space stays sorted, and we can continue to do choppings. So that is how binary search operates, right? So what would we do? Let's think about the time complexity. For every row, big O rows times what? What is the work I'm going to do in each row? Well, binary search runs in logarithmic time, upper bounded asymptotically. So we would be doing a logarithm of the columns in the matrix, right? Every row would have a certain number of columns we're going to search against. So we would do rows times log of columns, or big O of m times log of n. So I don't have notes for this video, so I'm going off the top of my head, so I'll probably catch any mistakes in editing. But that is what's going to happen if we do a binary search on every row. But there's a problem here. I mean, immediately I saw this, when I first saw this problem, I saw the little trick we could do, but let's say we don't notice where the trick is in this problem. Let's look at the time complexities. Put them right there. Those are the asymptotic bounds, or the class of common asymptotic bounds we normally work with. We see we have our linear time, we see we have our logarithmic time, we have n log n time. So where we're sitting at right now is right around n log n. We have 2 variables, so technically it's not n log n. But can we do better than this? Can we do better than this? Could we jump to linear time? Or could we jump to something that is logarithmic in some sense? So, in fact, we actually can do that. And one special thing that I want you to notice is the 2 special properties that were given to us. One, the rows are sorted. Number two, the last element in every single row is less than or equal to the first element in the following row. What does that mean for us? So this is a mental jump. I need you to make this mental jump because we can't see how we find the optimal solution unless we can really see this pattern. So I have this matrix shaped like this, and I purposefully gave each cell a number like that. This is the indice. That is the index. I don't even know if indice is a word. Someone told me that wasn't a word. Each of these cells signifies a index. And you see a two-dimensional array, but in fact, we know that the data does not dictate the way we interpret it. We saw that in heap sort. We had an array, but our visualization, the way we interpreted the data was not how the data was formatted in memory. We had a mapping system. We had a visualization system, right? And here in this problem, we have a very similar thing to that. We have a 2D matrix, but what I want to see is a one-dimensional array. I want to see a one-dimensional array because if I can see a one-dimensional array, I can perform binary search on that one-dimensional array. So think about this. We have m times n items, rows times columns items. If I were able to turn this 2D matrix into a 1D array, I am going to be able to chop m times n items in half. Chop, chop, chop in half. And then my time complexity becomes log of m times n. Log of the total items. How many times can I cut m times n items in half? Log base 2 of m times n. Again, this is logarithms, and we have videos on that explain logarithms, but that allows us to go logarithmic. Remember how I said, if we have a sorted array, the optimal solution, if I do not see logarithms in it, there's a problem, and I'm probably missing something. So, okay, we can go logarithmic in time, but my problem, the only hitch to this problem is our mapping system. So how do we generate a mapping? And it's actually kind of tricky, but whenever we try to do something with wraparounds and with arrays that map indices to where we need to wrap around between different arrays, we normally use a division sign and a mod sign. So this is what the equations look like right there. So our row, if you give me an index, to find the row I'm in, I need to take the index divided by the number of columns. So think about this. 6. 6 divided by the number of columns, 4. 6 divided by 4 is the same thing as 3 divided by 2, which is going to be 1.5. And we're going to truncate the decimal place because these are not floats, these are integers. Truncate the decimal place, and now we have 1. What row is 6 in? Row 1. Now let's try another example. So the 10 divided by the number of columns. 10 divided by 4 is the same thing as 5 divided by 2. So what we're going to have is we're going to have 2.5. So 2.5, truncate the 5, get the 5 away. We have row 2. So again, we can do 11 divided by 4. 11 divided by 4 is going to be something like 2.75, right? Remove the 7.5 and we get 2, the second row. So it would take a little thinking, it would take a little playing to see that we use the division sign to find the rows. And that's fine, because if you really think about it. If we're trying to find the row that an item sits in, the row that an item sits in is contingent to how many items we put in a row. Again, the row that an item sits in is contingent on the amount of items we can fit in a row. If I can fit 4 items in a row, that's going to affect the row an item sits in. Because the less items we can put in a row, the farther down our item probably will be, if that kind of makes sense. That's kind of explaining the intuition behind the rows. And now let's explain the intuition behind the columns. Why do we use the modulo? Why do we use mod? Let's first validate our calculations. So if I'm sitting at 6 again, if I do 6 mod 4. 6 mod 4 is going to leave us a remainder of 2. And what column is 6 in? It's in 0, 1, 2. Yeah, that's correct. So if we have 11, 11 mod 4. Well, if we do 11 divided by 4, our remainder is going to be 3. What column is 11 in? We have 0, 1, 2, 3, column 3. This is just kind of one of those things where you'd have to draw the pattern. Like 0 mod 4 is 0. 1 mod 4 is 1. 2 mod 4 is 2. 3 mod 4 is 3. And then 4 mod 4 will bring us right back to the beginning, right? So I think the best way I can explain this is if we are adjusting for wraparound, we're going to use the mod operator because mod helps us with wrapping around a fixed sized, section or fixed sized array / thing, right? And that's how we generate our mapping system. So we have a row and column mapping system. And now that we have our mapping system, it's just a matter of doing the binary search. So what we can do here is, why don't we actually execute a binary search? This will be fairly fast. So what I want to do is, I want to search for the number 7. So we're looking for 7. So what happens is, I set my left and right bounds. So I set my left at 0. I set my right at 11. So all the time, this whole time, I speak in one dimension. But I have my mapping system to take me to 2 dimensions at all times, So what we need to see is, okay, 0 and 11. So now, what I want to do is, I'm going to calculate the midpoint. So the midpoint is just going to be, you can calculate the code in the description does it smarter, but it's going to be 11 divided by 2, which is going to be 5.5, and that's going to become just 5. So our middle element sits right there. Our middle element sits at that position. But how do we get that in terms of rows and columns? So we need to do our math. So we're going to find the row. We're going to do the 1D position, 5, divided by 4 is going to give us 1. So we're in row 1, and our columns are going to be 5, or 1D position, mod 4, which is going to be 1. So we're in row 1, column 1. It's that guy right there. So is that equal to 7? We're searching for 7. So we see that that's not equal to 7. So which way do we go? Do we go left? No, we don't go left. We would lose value. We need to increase value. So we go to the right. So our new bound for left becomes middle plus 1. It becomes 6. Our 1D coordinate 6. So 6 to 11. So, okay, now we need to do another finding of the midpoint. 6 plus 11 is 17. 17 divided by 2 is 8.5. Truncate the 0.5, we have 8. So how do we get to 8? We need to do our mapping system. We do 8 divided by 4 is 2. We're going to be in row 2, and 8 mod 4 is going to be 0. So we're going to be in row 2, column 0. So that guy right there. And I numbered it purposely this way so you can immediately see the position, but we still have to do the calculations. So what we need to see is, that's our midpoint. Did we overshoot or undershoot? 8 is greater than 7. I need to go to the left. So let's go to the left. We need to move our right endpoint 1 minus the midpoint because we need to move to the left. So we need to narrow it, and now we come to 7. So we're between 6 and 7. Our left and right bound in one-dimensional coordinates are 6 and 7. So let's find the midpoint. So 6 plus 7 is going to be 13. 13 divided by 2, 6.5. Truncate the 0.5. We're going to be at position 6. So position 6, what is that in terms of rows? So 6 divided by 4 is going to be 1.5. We remove the 0.5, we see we're in row 1. And we're going to do 6 mod 4, which is going to leave us with just 2. And we're going to be in column 2. And that's correct. Row 1, column 2. And we're indexing off 0. So what we see is we undershot in value. 6 is less than 7. Go to the left. So our left point becomes 1 plus the midpoint. So now we have our right and left pointing at 7. We do our calculations, our midpoint's going to end up being 7, and bang, we found 7. That's the end of the search. If our left pointer went past the right, our search ends, we didn't find the item. So isn't this fascinating? We were able to take a two-dimensional structure and flatten it into a one-dimensional structure conceptually. We did not touch the array at all. But the special properties of the array allowed us to execute this. We were able to execute binary search. Our final runtime is big O of log m times n. Because we're going to have 12 items, we can cut 12 how many times? Log base 2 times. So we would be able to cut 12 to 6, 6 to 3, 3 to something like 1.51, and then cut it one more time down again. That is this approach. That is this variant. And now let's look at another variant and investigate further how we can take this searching story to another application and another type of 2D search. Okay, so now it's time to investigate a different variant on this problem where we have the same property on the rows. The rows are sorted going from left to right, and the columns are also sorted going from top to bottom. But the change here is that there's no guarantee that the last item in any row is related or less than or equal to the first item in the next row, right? So we can see an example of that. Look at the last item in the first row, 11. It's not less than or equal to the first item in the next row. So our visualization, gone. We can't turn this 2D matrix into a 1D matrix. There's no way we can do that because we can't draw the same relationships. We can't merge everything into one visualization, one conceptualized structure. We can't do that. We need to find another way to search this. So if this was the first variant you get, immediately you have the brute force. You have m times n. Again, we have the same amount of rows, which is 3 rows, same amount of columns, which is 4 columns. So same thing, m times n time, we upper bound to all the elements in the matrix. We're going to search every element and do constant time work at every element. So that's just m times n, upper bound. So let's think about this. We really need to do something that's critical when we're doing search problems. Whenever you get a search problem, the number one thing you think is, how can I reduce my search space? How can I reduce my search space? When we are looking at logarithmic problems, well, the way we reduce it is we chop it in half and we maintain an invariant. We maintain the invariance that the array is sorted. We chop it in half. So we can't really do the same thing here as straightforward. Well, the most optimal solution, sort of, it's like that. But we can't really do that here. So back to the drawing board. We need to rethink how we are approaching things. So let's do an example. Let's look for item 10. We're looking for 10. What I am doing is, at any point in time, what we're trying to keep in mind is, how do I reduce my search space? And a reduction of search space entails a decision. And in binary search, our decision is go left or go to the right, or go left to the right to you guys. But the decision is going to fundamentally bring us closer to an answer while maintaining the properties that the array is sorted. So what we need to think of is, what are the fundamental operations I can define to search this matrix? What are the I keep saying fundamental, I'm going to stop that. What are the core things, the core choices I can make at any step to reduce my decision space? That means we need to take a forking in decisions. We need to either go lower in value or go up in value. So, okay, we need to go lower in value or up in value. I said that. We need to keep that in mind. So how do I go up in value? Well, we need to think about this. This matrix is gradiented. There are gradients on it. There are gradients going from the left to right because the rows are sorted. There is a gradient running from top to bottom because the columns are sorted. And remember how I said we need a fundamental decision. So what we need to see is, we need to see that if I go left to right, I increase value. If I go right to left, I decrease value. If I go top to bottom, I increase value. If I go from bottom to top, I decrease value. So let's put that right there for reference. And what I just established there is something, I mean, it's right in front of us. It's not something where we would need to think too hard on it. It's given by the problem. These are actions we can do to reduce our decision space. And whenever we're doing a search problem, we are looking for a reduction of the decision space. And that's our desire. That's our desire to solve this. So what we need to think about is we need to think about how do these decisions play in to finding the most optimal solution. And what we're going to achieve is we're going to be able to achieve a near optimal solution. The most optimal solution is fairly involved, and it's actually addressed by cracking the coding interview. It's not in the code sample because it's fairly lengthy, but we're going to address the very close to the most optimal solution here, which is a linear time reduction of the search space with respect to the rows and columns. So how is this achieved? So follow me, think about this, and stay with me here. If I am looking for the item 10, what position do I need to place myself so I can express my abilities to decide to narrow my search space? So let's think about this. Let me try starting from the bottom left. So if I start from the bottom left, what can I do? I can go up in value, I can go this way. I can go down in value, I can go this way. Okay, yeah, that works for me. What if I start at the top right? I can go up in value, I can go down, and I can go lower in value. I can go this way. Okay, that works for me. Those are two places we could start. This is theoretically possible. Now let's try something else. Let me start at the top left corner. If I start at the top corner there, what can I do? I can go up in value, but then I can go up in value. So do you see how if I start at the top left, I'm not able to express my core decisions like I can do here, like I can do there. If I start at the bottom right, I can go lower in value, or I can go lower in value. So do you see the problem with the top, this corner and that corner? The problem with those is they don't allow us to narrow our search space. They don't allow us to narrow it in a valid way where we wouldn't need to search everything. So follow me. We're going to do an example, and you'll really see why the core thing we can do here is starting here or up there, and why our decision or our operations allow us to stay within ability to find our answer. So let's start at the bottom left corner. So we're starting there. Is 11 greater than or less than 10? 11 is greater than 10. So immediately, what do I understand? 10 cannot be in the last row. It only gets worse. It only gets worse in the last row. 11 is the smallest quantity in that row because it's the first quantity. And going to the right, I only can go upwards. 10 can't be there. 10 cannot be there. So let me express my abilities to decide. I decide to go down in value. How did we establish we go down in value? Well, we're going to go up, right? We're going to go that way. So we're going to come to the 8. Is 8 greater than or less than 10? And again, if it equals 10, we just return true. 8 is less than 10. Okay, what are my decisions? I can go up, which is going to decrease value, or I can go this way. I can increase value. So I want you to think about this. If 8 is in the middle of the column, can 10 be above 8? No, it's impossible. Why? The column is sorted. 10 cannot be above 8 because we lose value. So what you need to see is we're at 8. The only way to go is to go up in value. How do we go up in value? We go this way. Now we're sitting at the 9. Again, 9 is less than 10. If I go upwards, I can't do anything. 10 cannot be up above 9 because we lose value. We need to keep going. And then we find 10. So we found 10, and okay, that works. So my theory was right, and now we need to look at the top right corner. So let's start there, at 11. So let's look for 10 again. We're going to look for 10 again, and what we need to do here is we need to look how 11 relates to 10. So 11 is greater than 10, so I need to lose value. If I go downwards, I increase value. I'm getting farther away from the answer. I'm losing time, I'm wasting time. That's not going to get me to the answer. So what I need to do is 11. I need to reduce value. I need to come this way. I jump to my 7. 7. Is 7 greater than or less than 10? 7 is less than 10. I need to increase my value. If I go left in the same row, I'm getting worse. I'm going to go from 7 to 6 to 5 to 4 possibly. I'm not going to get 10. I need to increase value. So what we need to do is we need to go down. And we literally reduce or eliminate the whole row. And then we are sitting at 10. And that's our value we want, right? What we're doing here is we're reducing the search space at every step in the problem. And we're not breaking anything because it is impossible. It is impossible for the item to be in any of the positions that we just established that it cannot be. There's nothing we're doing. We're not breaking any rules. We're not saying it might be over here and it possibly could just be over there. It is literally impossible that the 10 could be to the right of that 11. Why? Because we know that that row is sorted, right? So that's what this solution is all about. Okay, yes, that makes sense. So what I need to do is I need to analyze this. So what is the worst work I can do? And I mean, really think about what we were just doing. We were going either up or this way, or we were going down and this way. What is the farthest I can go left or right? Well, the farthest I can go left or right is the amount of columns, n. What's the farthest I can go up or down? The farthest I can go up or down is the amount of rows. So we can upper bound the total amount of operations to be at worst, the total operations we do is the number of rows plus the number of columns. And the reason that's the case is because at worst, we're doing little shift operations, shift over. At worst, I can shift this far and I can shift this high, right? So that's why we add. It would come to a concrete value. So actually, let's find the concrete value just to really nail this in. So if I went all the way, that would entail 1, 2, 3, 4 checks, which is 4, that's how many columns we have. And then if I went upward, we would do 1, 2 checks. And then we might not find the item, but how many checks did we just do? 1, 2, 3, 4, 5, 6. 6 checks. What is the rows plus the columns? Or what are the rows plus the columns? Well, we have 7 total. 4 plus 3 is 7. So that is an upper bound. That upper bounds the amount of operations we could do. So asymptotically, we say big O, m plus n. Now, there's actually an even faster solution to this, and that is actually a very lengthy solution. It's addressed in Cracking the Coding interview. I put it in the code in the description, and it's very lengthy. And like I said, if you don't see a logarithm in your time complexity and something is sorted, then there's you probably don't have the most optimal solution. So it does run in logarithmic time with respect to the rows and columns, but I'm going to leave that for another time because this video is already very long. So yeah, that is how you search a 2D sorted matrix, and yeah. So that is all for this video. If you like this video, hit the like button, subscribe to the channel. My goal is to build one of the world's largest software engineering resources. It might never become the largest, well, probably won't, but I want it to be one of the world's largest software engineering resources because I think we just need more resources in this space of stuff, and I think it's a cool thing to do. And yeah. I always think, like, is this stuff useful? Kind of isn't. I mean, it kind of makes you think harder. But I mean, I still feel like